Alright, so let's get started with mole's second worksheet. So we will need to understand mole conversion. We will need to know the mole rules, like we need to know that uh, in moles, the ratio of moles is same for gases as the gas volume. So the ratio of gas volume is the same as ratio of moles. And that is what we are going to use in the first question. So the first question says that 10 cm cube of propane, which is this compound here, is burnt in 70 cm cube of oxygen in a closed container. Okay, so that means there's no more oxygen coming in from there. What is the total volume of gases present after the reaction? Now let's look at the mole ratio. If you have 1 of this, it produces 3 of carbon dioxide by reacting with 5 of oxygen. And water here is obviously liquid. So I just have 3 gases to look at. Now if 1 reacts with 5 to make 3, 10 will react with 50 to make 30, which leaves me with 70 minus 50, 20 cm cube of oxygen, that is extra, that is in excess, that is left over, and 30 cm cube of carbon dioxide, which is made up. So that gives me 50 in total. So my answer is B. When a mixture of sodium chloride and sodium hydrogen carbonate is heated, the reaction shown takes place. Okay, so sodium hydrogen carbonate, as you know, will break down, produce carbon dioxide, water, and sodium carbonate. Sodium chloride is unchanged on heating, which means the sodium chloride does not break down. So sodium chloride is thermally much more stable than sodium hydrogen carbonate. When 6 grams of the mixture is heated, the loss in mass is 1.5 grams. Now, where is the mass loss coming from? We know law of conservation of mass. Mass shouldn't change in a chemical reaction, but what's happening here? Basically, these are the gases, and these gases leave it. Okay, so that means that 1.5 grams of gases leave the substance, the solution that you have. All right, and if you come to think of it, that is 2 moles of gas. The mole ratio is that 2 moles of this solid produces 2 moles of gas, one for carbon dioxide and one for water. So judging by that, I can figure out that if I have 1.5 gram taken away, what is the average moles of this thing, or what is the way in which these are broken down. So let's suppose we have carbon dioxide and water. Their MR, when you collect them as a mixture, is going to be 44 for carbon dioxide and 18 for water. The total comes out to be 62. Now 1.5 divided by 62 is going to give us our number of moles of the gas that comes in, and if you multiply it by 2, that will give us the moles of sodium hydrogen carbonate that were taken out. Now if you multiply that by the MR of sodium hydrogen carbonate, which is 84, that will tell me what is the mass of sodium hydrogen carbonate, which comes out to be 4.06 grams. Now 4.06 grams is the mass of sodium hydrogen carbonate that reacted, divided by 6, which is the total, into 100%. And your answer is 67.7, which is 68%. Alright, the expression shown for the value of AR for fluorine is incomplete. Now remember that the definition of AR is that it is the average mass of one atom of every whatever element you're talking about compared with mass of one atom of carbon 12. And 1/12 of that carbon 12 will be a unit. So it's basically compared with 1/12 of the mass of one atom of carbon 12. So using that idea, we can take B to be our answer. In a volumetric experiment, 25 cm cube of 0.1 mole per dm cube sodium hydroxide. So notice that this is volume and this is concentration, but both of them are for sodium hydroxide. Now, what's the concentration of sulfuric acid? Now, there are multiple ways of doing this. We already know the volume of sulfuric acid, so we can use the mole ratios here, which is 2 and 1. And we can use the shortcut. The shortcut for any titration or any reaction where 2 solutions are reacting is Cv over N of the first one is equal to Cv over N of the second one. Here C is concentration, V is volume, and N is the mole ratio from the equation. So if I plug in the values here, let's suppose my left side is for sodium hydroxide, then I get C as 0.1, V as 25, and N as 2. And over here, I'll get C as the unknown and V as 20 divided by N as 1. Now notice that I did not have to convert 20 cm cube or 25 cm cube into dm cube because it's already taken care of because of the shortcut idea. And when I do that, my answer comes out to be A. What mass of carbon contains the same number of atoms as 16 grams of sulfur? Now, the first thing I need to know is what is the moles of sulfur here? Because every time they say what mass of carbon contains the same number of atoms, this is the key idea. Same number of atoms for anything that is uh, atomic as carbon or sulfur, then we are going to talk about number of moles, same number of moles. That's how we'll read it. So 16 divided by sulfur's AR, which is 32, is half a mole. So considering that half a mole of carbon is going to be 6 grams, because AR of carbon is 12. 3 dm cube of sulfur dioxide is reacted with 2 dm cube of oxygen. So we have 3 of this reacting with 2 of this. Okay, assuming the reaction goes to completion, that all gases are at which volume of sulfur dioxide is formed. Now, what is the limiting reactant here? Of course, we need 2 moles of sulfur dioxide to react with 1 mole of oxygen. And obviously, if I wanted to react with 2 moles of oxygen, I need 4 moles of sulfur dioxide, which I don't have. Which means that I will basically use my limiting reactant, and the limiting reactant here is sulfur dioxide. I can only use 3 of it. And if I use 3 of it, I don't need 2 moles of oxygen gas. I will just make do with 1.5. So 1.5 of oxygen is used up, and that produces 3 of this will produce 3 of this, because 2 produces 2. So I get 3 moles or 3 dm cube of sulfur dioxide. Now, why am I taking volume instead of moles here? Because volume ratio is same as mole ratio whenever you have gases involved. So this is Avogadro's law, and it really helps. Moving on, which row correctly identifies a different formula of ethene and of its homologous series? Now, you might study organic chemistry later on in the syllabus, but you need to know what empirical formula and molecular formula is. Empirical formula gives us the simplest ratio. Molecular formula gives us the actual number of atoms that are in the compound, and general formula tells us the pattern that it follows. So this is my empirical formula, because it gives me the ratio that for every carbon I have 2 hydrogen. This is my molecular formula. This tells me the actual number, and this is my general formula. It tells me the trend. So judging by that, A is my answer. Question number 8 says, what is the ratio of number of molecules in 71 gram of gaseous chlorine to the number of molecules in 2 gram of gaseous hydrogen? Now notice that we have gaseous chlorine, which is Cl2, and gaseous hydrogen, which is H2. And the MR for both of these is, this one is 2, and for this one, this is 71, which turns out to be the same mass as they have given. So the moles that I get is 71 over 71 ratio 2 over 2, which is 1 to 1 ratio. Ammonia is manufactured from nitrogen and hydrogen by the Haber process. You need to remember the conditions and everything for this. What is the percentage yield when 60 kg of ammonia is produced? So you have 60 kg of ammonia made, that's the mass, from 60 kg of hydrogen. You have 60 kg of hydrogen. Okay, so obviously 60 kg of hydrogen will not produce 60 kg. The numbers will be very different, because hydrogen is such a lighter thing, which means 60 kg will have so many number of moles. So I want to figure out my percentage yield, and percentage yield depends on 2 things. It depends on the practical yield which you have, which is 60 in this case. It also depends on the theoretical yield, like what would I get if I let this reaction complete, or if it reaction went to completion. So let's see, 3 moles of hydrogen produces 2 moles of ammonia. Now, how many moles is 60 kg? I'm going to keep the K out of this. I'm going to multiply it with K at the end. So 60 divided by 2 will give me the moles of hydrogen. So 60 divided by 2 is 30. So 30 moles, in fact 30,000 moles of hydrogen should produce 20,000 moles of ammonia. And 20,000 moles of ammonia is 20 times 17. So that's going to be 340 kilograms. That's what I should get. But I only got 60. So 60 divided by 340 times 100% tells me my percentage yield, which comes out to be B. Now this is the last MCQ here. A mass of 63 gram potassium manganate 7, which is a very good oxidizing agent, by the way. It goes purple to colorless when it reacts, is needed for complete oxidation of 23 grams of ethanol. So they're basically using it to oxidize ethanol under acidic condition. With acids, potassium manganate works better. How many moles of ethanol can be completely oxidized by 1 mole of potassium manganate under these conditions? Now, we don't have an equation for ethanol and KMNO4 reacting, and we don't really need it in O levels or IGCSE. But what we do have is the mole ratio. Wait a minute, we don't have mole ratio, we have mass ratio. But that's the same as mole ratio to us because we can convert it to mole ratio. So I'll divide 63 by the MR of KMnO4 and I'll divide 33 by the MR of ethanol. When I do that, I get my mole ratio. So then they're saying how many moles do I need for 1 mole of KMnO4 to react. So if I have KMnO4 here and I have ethanol here, then 23 over its MR, which is 46, should give me the moles of ethanol, and 63 over its MR, which is 158 for KMnO4, should give me its moles. And this is going to be, if I have 1 mole of this, then how many moles of ethanol will it react with? Cross multiply and you get your mole ratio, and that comes out to be 1125. There you go. Calculate the mass of oxygen in 11.5 dm cube sample at room temperature and pressure. So at room temperature and pressure, we know that 1 mole of any gas takes, so 1 mole of any gas is going to take 24 dm cube at room temperature and pressure. So let me just use the mole ratio to figure out how many moles I have of this thing. So 1 mole takes 24 dm cube, so 11.5 dm cube will be for x moles. When I cross multiply, I get x equals to 11.5 divided by 24, which comes out to be 0.479 moles. Now moles is mass over MR, so 0.479 equals to mass, which is unknown, divided by MR of oxygen gas, and oxygen gas is 32 as the MR. So mass is going to be 32 times 0.479, which comes out to be 15.7 grams. Moving on, this compound breaks down to produce nitrogen and water, and we have 25 cm cube sample of, so that's the volume of 0.15 mole per dm cube, that's the concentration. Notice that this is a solution of this thing is heated. Calculate the maximum volume of nitrogen formed. So basically we want to figure out what is the number of moles of nitrogen formed, and turns out the mole ratio is 1 to 1. So we just need to know moles of this compound, so that is N equal to CV. So number of moles is 0.150, which is the concentration, times 25 over 1000. Notice that I'm dividing it by 1000 because I want to convert cm cube to dm cube, and when I do that, my moles come out to be 3.75 into 10 power minus 3. Now once I have that, I can use the ratio that 1 mole of this thing produces 1 mole of nitrogen. So 3.75 into 10 power minus 3 moles will produce the same amount of nitrogen gas. Now 1 mole of any gas produces 24 dm cube at room temperature. So 3.75 into 10 power minus 3 will produce x. And when I cross multiply, I get my x equal to 0.09 dm cube, and that's my answer. Okay, this part is saying calculate the maximum mass of iron formed. So we are looking for maximum mass, which means it's the 100% yield of iron formed, which is the product here. When 12.5 grams, so this is 12.5 grams, that's the mass given, of iron 3 oxide reacts with excess carbon monoxide. So carbon monoxide is in excess, we don't need to worry about it. But we do have mole ratio of iron oxide and iron. So the first thing we should do is figure out how many moles of iron 3 oxide do we actually have. So MR of iron 3 oxide is what we should start with. So MR is going to be 2 iron plus 3 oxygen. You plug in the values, 2 times 56 for iron plus 3 times 16 for oxygen, and you get your answer 160. Now that is the 160 grams of 1 mole iron 3 oxide. I have 12.5 grams, so number of moles is going to be 12.5 divided by 160, and that's my number of moles of iron 3 oxide. But my mole ratio is 1 to 2, which means if I multiply this by 2, I get my moles of iron that I'll get. And I want to figure out the mass of that thing. So this value, what I'll get, I'm going to multiply it by, so this is 0.078. I'm going to multiply 0.078, which is the number of moles of iron, by 56 because I want to figure out the mass of iron. And that comes out to be 4.38 grams. Notice that I rounded it off to 3 significant figures. Alright. Dilute sulfuric acid reacts with aqueous sodium hydroxide. You have a solution here reacting with another solution. Now again, for two solutions, we have multiple ways of solving them, but the shortcut is always the best idea because it helps you take care of the unit conversion, because you don't have to divide by 1000 to convert cm cube to dm cube. Similarly, because this is usually a three-step process, it reduces the number of steps that you have, so you can clearly see where the values fit in and what is that relation between them. So I'm going to use that. I want to figure out Cv over n of solution 1 equal to Cv over n of solution 2. Again, concentration, volume, and number of moles comes from the equation. Let's say this in my solution 1 is acid. So I don't have the concentration of the acid, but I do have volume of the acid, which is 25 cm cube. Divided by, the ratio from the equation is 1, so I write 1. And concentration of sulfuric acid is 0.0150. And this multiplied with 24 cm cube of sodium hydroxide volume divided by mole ratio, which is 2. Now notice that I did not divide by 1000 here, because even if I do 1000 here and 1000 here, this is going to cancel out anyway, so I don't really need to do that. So once I do this, I get 0.015 times 24 over 2 times this 25, which came from there to here, to divide, and that gives me my final answer, which is going to be 7.2 into 10 power minus 3 mole per dm cube. Make sure that you either write it in standard form or you write it in the complete as a number like 0.0072. Alright, fluorine reacts with aqueous sodium hydroxide to produce sodium fluoride. Calculate the maximum volume of oxygen produced. So this is the key important element here. At room temperature pressure, when 0.037 mole of sodium hydroxide, so 0.037 mole of sodium hydroxide completely react with fluorine. That means fluorine is going to be completely reacted. We don't need to figure out its moles. So the moles that we need to focus on is 4 moles of sodium hydroxide making 1 mole of oxygen. So if I have 0.037 of this, I get x moles of oxygen. Alright, so I cross multiply. X comes out to be 0.037 divided by 4, and that's my number of moles of oxygen that is being produced, and that is 9.25 into 10 power minus 3. Now I know that any gas takes 24 dm cube at room temperature and pressure, and that is what they've given us. So 1 will produce 24 dm cube. So I have 9.25 into 10 power minus 3, that will produce x. When I cross multiply, I get my volume, which is 0.22 dm cube, and that's my answer. Moving on. The question says calculate the maximum mass of aluminium formed when 25.5 grams of this thing reacts with excess magnesium. So magnesium is in excess, I don't need to worry about it. I will still need to know the moles of aluminium oxide, because from there I get to know the moles of aluminium. So for that I need MR of aluminium oxide. So MR of aluminium oxide is going to be 2 aluminium plus 3 oxygen, which comes out to be 102. Now my moles of aluminium oxide is going to be 25.5 divided by 102, because that's how I figure out the number of moles, and this is going to be 0.25. And this number, I will then use it for mole ratio. So this is the moles of aluminium oxide that is made, and 1 mole produces 2 moles of aluminium, as you can see over here. Then 0.25 will produce x of this, which comes out to be 0.5. So x is 0.5 moles of aluminium that is made. Now 1 mole of aluminium is 27 grams. It is the AR of aluminium. So 0.5 will be 27 times that, and that gives me 27 times 0.5, which is 27 over 2. You can write it like that, or you can write it as 13.5 grams. Alright, let's look at this question. Dilute nitric acid, again a solution, reacting with another solution to produce another soluble salt. A student titrates. Again, titration is just another word for reacting two solutions carefully. When you have the volume and everything here, I'll just use the shortcut again. So Cv over n of one solution is equal to Cv over n of the other solution. This makes it really easy to solve this. Now, notice that you have 25 cm cube of dilute nitric acid. So you have 25 of this but you don't have the concentration, and the number of moles from the equation is 2. It's basically the mole ratio. Similarly, you have 0.045 here times the volume, that is to 34, divided by the number 1. You solve this comes out to be 0.045 times 34 times 2 divided by 25, sorry, and that gives me 0.1224 mole per dm cube, and that's my answer. Now, if I wanted to do it without using this shortcut, then what I'll do is that I'll first figure out number of moles of what I actually know. So I know the number of moles of barium hydroxide. So number of moles is concentration times volume. This is my first step, okay? So that's going to be 0.045 times 34 divided by 1000 to convert it to dm cube. Now this is my number of moles of barium hydroxide that I have. Now using the mole ratio, I'll multiply this number by 2. So 1 barium hydroxide reacts with 2 moles of that. So 0.045 times 34 over 1000 reacts with X. So you'll notice that this number multiplies with 2. By the way, you can clearly see that happening over here. So it multiplies with 2. After it multiplies with 2, I have to divide it, or basically use n equal to cb again. This is my third step. This was my second step. This is my third step, because I have the number of moles here and I have to divide it by the volume. So this volume comes here. So number of moles over volume is equal to concentration. The volume is 25 and the number of moles is this number times 2, which is basically this whole thing again. So that gives me 0.1224. So 0.1224 mole per dm cube, and that's my final answer. So that brings us to the end of the second worksheet. This was all about mole conversion, empirical formula. We have already discussed yield now, and we will talk about further concepts of mole in the next worksheet. So I'll see you in that one. Take care. Bye.